not 1.09, it's 109.
Where'd you get the point from?
I don't know. Kept thinking about ruining or something.
You ready?
Yeah, let's do this.
Ooh. Let's try to make this a clean shot this time.
Okay. Take two.
Do this. Do this. Take two. Take two, everybody. I'm gonna put this in the bloopers. See if we can make that a thing. All right, 3, 2, 1. Hello, everybody. This is Drew Castro and Tommy Rodriguez.
How you doing?
We did our physics project on how changing the wavelength of a string affects its frequency, specifically on a guitar string. Now, when you play a string on a guitar, you hear a certain pitch. By playing the first string on this guitar, you hear the note E. That pitch has its own specific frequency, and it's moving at a specific speed. But when I push down on the string on another fret, which is what this piece of wood is divided into, frets, the pitch becomes higher. First it is E, then it is G, and then it is A. Through this, we can assume that changing the wavelength, which is the distance, or the entire length that the wave flows through, by changing that, we are affecting the frequency. In this particular case, we believe that shortening the wavelength will increase the frequency and maintain the same speed. And in order to do this, we use the equation frequency times wavelength is equal to speed. Now, through this, we were able to figure out that we used 6 different notes in particular in order to test this theory out. We use the notes E, G, A, B, F sharp, and B flat. These are all notes found on the E string depending on where you place your finger over the frets. In order, we found that E has a frequency of 82.41 Hertz, F sharp has a frequency of 92.5 Hertz, G has a frequency of 98 Hertz, A has a frequency of 110 Hertz, B flat has a frequency of 116.5 Hertz, and B has a frequency of 123.5 Hertz. Now, we figure that each of these notes have an increasing frequency. So the higher the note, the higher the frequency. This alone aids us in solidifying our previous hypothesis. But just to try it out, I'm going to play those notes to make sure that each of those notes are higher than the last. So E, then F sharp, G, A, B flat, and B.
Okay, so we found wavelength by the length of the string, multiplying it by 2 to get the entire period. So as we calculated it, we got around the same speed as 109 meters over seconds.
So for each of these notes, it moved at a speed of 109 meters per second. So the string vibrated at the same speed for each of those notes. Through this, we find that speed was not a factor in changing the frequency, even though the frequency was getting higher. The only other thing that we can conclude is that changing the wavelength affected the frequency. But we're not going to just leave it at that. We are going to display this using YouTube, of all things. Now, as we said before, for E, G, and A, their frequencies are 82.41, 98, and 110. Just to make sure that these are accurate, we are going to play those frequencies, and I'm going to match them on the guitar.
Okay, this is for E. And now this is for 98 Hertz.
G.
G. And now this is for 110 Hertz. is for
A. I swear we didn't fart. I swear. You try that one again?
Let's see this one more time. One more time. One more time. One more time. We got this.
I swear that was not intentional. We're not cutting that out. Alright, so through this we can find that. You guys can hate me for that later. Each of those frequencies was increasing, and each of those wavelengths were getting shorter. So, in conclusion to our research and the actual equations that we had to do in order to find this information, we can figure out that by shortening the wavelength, we are increasing the frequency. For the sake of argument, we did not include the weight of the string or anything like that. That's why we found each of the speeds specifically, so that wouldn't be an issue. But as for our project, that should be all. Thank you very much for your time. See you in class.
Bye, everybody. Rock and roll.